Hello everyone and welcome to our final module video on software development. In this module we will explore the software evolution process in detail. We will begin by understanding what the software evolution process is and why it is essential. Next we will differentiate between evolution and servicing, followed by discussion on the evolution process and its key activities. After that, we will dive into legacy system, then move on to the software maintenance, where we will discuss maintenance costs and complexity metrics. We will also cover software engineering and refactoring. And finally, I will provide you with a summary of what to expect on the final exam, including its structure and the types of question you might encounter. So let's get started. I will begin by discussing what software evolution is. Software evolution is a fundamental process in software development that refers to the ongoing development, maintenance, and adaptation of software after its initial release. Unlike the initial development phase, software evolution ensures that the system remains functional, relevant, and aligned with the changing needs of its users and the environment. Now, why is software evolution so important? In general, this process is critical because software needs to be continually updated and improved to meet changing user requirements, adapt to new technology, and fix bugs or security issues. So we have here first new requirements emerge as the software is used in real-world scenario. This may include new feature or functionalities that user request. Second, the business environment changes. Company evolve and their software needs must adapt accordingly. Third, bugs needs to be repaired. Even the best software requires fixes over time to ensure reliability. Fourth, new computers and equipment are often added to the system, requiring updates for compatibility, for example. And finally, the performance of the system may need improvement to meet the higher demands or deliver a better user experience. So, without software evolutions, systems risk becoming obsolete or ineffective. Additionally, it is worth noting that the majority of the software budget in large companies is devoted to changing and evolving existing software rather than developing new software. For example, think about Facebook. They developed the initial platform once, but they continuously evolve it by adding functionality and improvement. This process will continue as long as the platform exists. Let me now introduce some important terms related to software development, which are evolution and servicing. I will explain these concepts in the context of the following diagram, which represents the life cycle of software product. This cycle can be viewed as consisting of four distinct stages. The first stage is initial development. This is where creativity comes to life. Ideas are born, requirements are gathered, and the prototypes are developed. It's the foundation where the software begins its journey. Next is the evolution stage. At this point, the product is out in the market and no longer just a prototype. Here we continuously refine and adapt the software based on user feedback, market needs, emerging trends. New features are added, functionality is improved, and the product evolves to remain competitive and relevant. Then we enter the servicing stage. At this point, the software is stable and functional, but changes are limited to essential maintenance. This includes bug fixes, and updates needed to keep the software operational in a changing environment. No new features or major updates are introduced in this stage. Finally, we reach the phase out stage. This is when the software is retired and no further changes are made. It may still be used by some users, but the focus shifts to making room for newer and more innovative solutions. So, let me highlight the key differences between evolution and servicing again. Evolution is about growth, adding new features and improving functionality to stay competitive. Servicing, on the other hand, focuses on maintaining the software's usability without adding any new features. Understanding this difference is important because it defines how resources and efforts are allocated in the software lifecycle. Now that we have introduced the lifecycle of a software product, let's dive deeper into the software evolution processes and how they vary based on several factors. First, the evolution process depends on the development process used. For example, whether the team follow an agile methodology or a traditional waterfall model can significantly influence how changes are managed. For example, in Agile, a mobile application team might quickly add a feature, let's say a dark mode feature, in a 2-week sprint, based on user feedback. In contrast, a banking software team using Waterfall would require detailed documentation, impact analysis, and formal approvals to add a similar feature, making the process slower but ensuring stability. Second, the skills and experience of the people involved play a critical role. Experienced developer and teams may handle changes more efficiently and adapt better to unforeseen requirements. Third, the type of software being maintained is also a factor. For example, the evolution of mobile application is often informal, with quick updates driven by direct interactions between developers and users. On the other hand, critical embedded systems, such as those in medical devices or aircrafts, require a more formal and structured evolution process with detailed documentation and approvals at every stage. A key driver of software evolution is proposals for change. These proposals must be linked to the specific components they impact. This linkage enables teams to estimate the costs and the impacts of the changes effectively. Understanding this helps prioritize changes and avoid unnecessary disruption to the system. Finally, change identification and evolution continues through the software's lifecycle. This is not a one-time process, but an ongoing cycle, or let's say, it's a loop that will keep repeating over all as far as the software exists, it will keep looping to ensure that the system stay relevant and function. The software evolution process journey begins with a new software or a new system, which is developed and deployed to fulfill initial requirements. Over time, as the system is used, new needs arises or issues are identified, triggering the next process, which is change identification process. At this process, the stakeholders, such as users, developers, and managers, recognize areas for improvement or necessary adjustment. This could include new features, bug fixes, or system optimization. The output of this process is change proposals, which document specific suggestions for changes. These proposals serve as an input for the next process, which is the software evolution process, where the proposed changes are implemented. Once the changes are implemented, the result is essentially a new system. And the cycle begins again. This iterative process ensures that the software continuously evolves to meet changes requirements throughout its lifetime. So this diagram emphasizes what I mentioned in the previous slide, which is that the process of change identification and system evolution are cyclic and continuous throughout the entire lifetime of the system. Let's talk in details about the software evolution process, which consists of mainly four activities. The process evoked by a change requests. Then, the first activity, which is impact analysis, starts by assessing the cost and the impact of these changes to see how much of the system is affected by the change and how much it might cost to implement the change. If the proposed changes are accepted, a new release of the system is planned. During this phase, all proposed changes such as fault repairs, platform adaptations, or the addition of new functionalities are carefully considered and prioritized. Example for platform, I mean, fault repair is clear, system enhancement are clear, but what we mean by platform adaptation, think about if a company upgraded its server from Windows-based platform to a Linux-based platform. The software running on these servers might need modification to ensure compatibility. Then we start to implement these changes and keep iterating over multiple releases until all planned changes are completed. Finally, after the changes are successfully implemented and validated, a new version of the system is released, ensuring that the system evolves to meet updated requirements and maintain functionality. At this time, we are waiting to the next change request to keep cycling over and over again. Change implementation, which is a critical part of the software evolution process, involves an iteration of the development process, where revisions to the system are designed, implemented, and tested. However, there is a key difference here. The first stage of change implementation often include a program understanding phase, particularly when the developers implementing the changes are not the original system creators. During the program understanding phase, it is essential to gain a clear understanding of how the program is structured, how it delivers its functionality, and how the proposed changes might ripple through the system and impact other parts of the program. So we can say that the change implementation process can be divided into two main phases. The first one is program understanding phase. This is where we analyze the software's architecture, study its functionality, and carefully assess the potential effect of the proposed modifications. And this phase ensures we know exactly what we are working with before making any changes. The second phase is the change implementation phase itself. This is where we actually implement the required changes, followed by thorough testing to validate that the modification work as intended. You can see here two models for change implementation. The first model represents the original change process. In this process, we start with requirement analysis, where we may go back and forth to refine and reformulate the proposed changes. Once the changes are finalized and agreed upon, we move to the requirements updating activity, where we update the requirements document. And finally, we proceed to the software development activity, which includes all the familiar steps such as designing, implementing, and testing. However, there are situations where we may need to perform an emergency repair for a critical issue. In such cases, we follow the second model, which is for urgent changes. These changes are implemented without going through all the standard stages of the software engineering process. Example of emergency repairs include fixing a serious system bug that is disrupting normal operations, addressing an unexpected effect caused by change to the system environment, such as operating system update, responding rapidly to business changes, like releases of a competing product that require immediate action. In this emergency model, the process begins by directly analyzing the source code, making the necessary modifications, and delivering the modified system as quick as possible. There is no time to update the requirement document or the specification document. Here, it's an emergency change. We need to get it done as fast as possible. Now that we have discussed the change implementation, it is important to recognize that not all changes are straightforward, especially when dealing with older systems. In many cases, the process of implementing changes become much more challenging when the software we are working with is outdated or tied to older technologies. This brings us to our next topic, which is legacy systems. Legacy systems are older systems that rely on languages and technologies that are no longer commonly used in new system development. For example, you might encounter software written in Fortran or Pascal language, which was widely used decades ago, but is now considered outdated. People replaced it with Python or Java, and I'm sure that even most of you didn't hear the name of these old programming languages. These systems are often dependent on older hardware, such as mainframe computers, and come with associated legacy processes and procedures that were designed to support the original system environment. It is also important to note that legacy systems are not just about the software. They are broader integrated systems that include the hardware required to run them, software libraries and other supporting tools, and even the business processes that were built around the system's original functionality. A classic example here is banking systems. Many banks still rely on legacy systems running on mainframes for core operations like transaction processing. While these systems are reliable, any change, like adding new online banking features, requires significant effort because they are deeply integrated with old hardware, software, and business workflow. As we move forward, we will explore why organizations continue to use these systems and the challenges they pose when adapting to modern requirements. Let's now look to the component of a legacy system and how they are interconnected. At the center, we have application software, which is the core of the system that provides business services and delivers the functionality that users rely on. Usually, it is made up of a number of application programs. However, this software does not operate in isolation. It is closely tied to several other components. The application software uses and interacts with large amount of data. This data is often structured in ways specific to the legacy system, creating challenges for compatibility with modern tools. This data may be inconsistent, duplicated, or held in different databases. Also, the application software uses other support software. This includes tools, libraries, or middleware that the application depends on to function. Sometimes this tool may be obsolete or unsupported. Legacy system and its support software often runs on older hardwares that may no longer be available or supported. This dependency can make upgrading or migrating the system challenging. Moreover, business policies and rules that constrain business process. Use of legacy application system may be embedded in these policies and rules. For example, in banking system, legacy application may enforce policies like loan approval rules, such as verifying credit scores and income thresholds. These rules are embedded in the system, ensuring compliance with business rules. Replacing or updating the system requires re-implementing these policies, and maybe these policies are not written or documented anywhere else, which will be a real problem. I believe you now understand why legacy systems with all their integrated networks are so complex and challenging to replace. Since these systems are so old, we are left with two alternatives. Either replace the system or make changes to it. Let's explore the first option, which is replacing the system. Please pause the video for a moment and try to answer this question based on your understanding. Why is legacy system replacement risky? Of course, the first reason because of lack of complete system specification, tight integration of the system with business processes, undocumented business rules embedded in the legacy system. This is similar to the examples I mentioned in the previous slide of the loan approval banking system. New system or new software development may be delayed or over budget. Now let's discuss the second option, which is making changes to the legacy system. Although this might seem like a simple solution, you will find it to be very expensive. Again, please pause the video for a moment and try to answer this question. Why is legacy system change expensive? First, there is no consistent programming style because multiple developers work on it. Use of obsolete programming language with a few skilled developers available. For example, during the lead up to the year 2000, also known as the Y2K problem, there was a high demand for COBOL programmers. Many older systems still in use at the time were written in COBOL, and it need to be updated to handle the data change from 99 to 00. These programmers were paid very well because they were rare and the problem was really significant. Inadequate system documentation. System structure degrade over time because of keep changing it over time. I can think about two other things or reasons that make it expensive, like program optimizations that make the code harder to understand, and of course a lot of data errors, duplication, and inconsistency. These factors make both replacing and changing legacy system challenging and require careful planning and consideration. Now that we have discussed the challenges of changing or replacing legacy systems, I'm sure many of you are asking, what should we do then? Change or replace? To answer that, let's consider 10 legacy systems and divide them into 4 categories based on their quality and business value. The first group is a low quality, low business value. These systems are unreliable and don't contribute much to the business. Example for this, think of an old vending machine that frequently break down, doesn't accept new payment methods like credit card or Apple Pay, and offer snacks that no one wants. Since it is unreliable and barely used, it is best to scrap it and replace it with something more useful. The second group is the low quality, high business value. These systems are critical for the business but are expensive to maintain due to their poor quality. Example for this, imagine a school bus that is always break down and running late. Despite its poor condition, it is essential for getting students to school. The solution here is to either re-engineer the bus or replace it with a newer one, which will be more reliable model. The third group is high quality, low business value. These systems are in good condition but don't provide much value to the business anymore. Example here, picture a well-maintained playground in a neighborhood where most children have grown up and moved away. It is still in great shape, but it is not heavily used. You could maintain it for occasional use or replace it with something more relevant to the community if maintenance becomes costly. And finally, high quality, high business value. These are the systems you want to keep. They are both well functioning and critical to the business. Think of modern coffee machine in an office that everyone uses daily. It works perfectly, serves a variety of drinks, and only need basic cleaning. For such systems, the best approach is to continue regular maintenance and keep them in operation. You can see here that by analyzing legacy systems based on their quality and business value, we can make informed decisions about whether to scrap, maintain, re-engineer, or replace them. This structured approach ensures that resources are invested wisely and aligned with the system's importance to the business. Let's now talk about software maintenance. Software maintenance is a process of tweaking or modifying software after it has already been deployed and is in use. Now, here is an important clarification. The term maintenance and evolution are often confusing because they seem very similar. The main difference is we use the term maintenance when we are talking about changes to custom-made software. On the other hand, the term evolution is more commonly used when referring to changes in generic or commercial off-the-shelf software. In software maintenance, there are three main tasks. The first one is fixing bugs, which is addressing errors or faults in the software. The second one is adaptation, which is making the software work on new computers, operating systems, or environments. And finally, adding new features, which is enhancing the functionality to meet new business requirements or user needs. These tasks are often overlapped. For example, adapting the software to a new operating system might require adding functionality or fixing bugs along the way. Let me now ask a question. What do you think is the cost distribution among these three tasks? Research shows that the distribution typically looks like this. 57% of the cost goes to adding new features. 24% of the cost is spent on fixing bugs. And 19% of the cost is used for adapting the software to a new platform or new system. But why does it break down like this? The largest share, which is 57% for adding new features, is because software often needs to keep up with changing business needs. market trends, or user demands. Organizations continually evolve, and the software must evolve with them to stay relevant and competitive. This is why feature enhancement dominant maintenance costs. Next, 24% for fixing bugs, which reflects the reality that no software is perfect. Bugs are discovered during real-world use, and addressing these issues is critical to ensure that the system is reliable and satisfying the users. However, since bugs are generally fewer over time, their share of the cost is smaller compared to new feature additions. Finally, 19% for adaptation, which highlights the importance of ensuring compatibility with new systems, such as operating system upgrades, hardware replacement, or updated frameworks. While adaptation is vital, it tends to occur less frequently, which is why it takes up smaller portion of the overall cost. This distribution emphasizes that the bulk of maintenance is not just about fixing what is broken, but about continually improving and evolving the software to meet the changing requirements. Since adding new features accounts for the largest share for maintenance costs, let's ask an important question. Which is more expensive? Adding new features during maintenance or during the initial development of the system? The answer is that it is typically more expensive to add new features during maintenance than during development. But let's explore why. First, when a new team is assigned to maintain the system, they need to spend significant time understanding the existing code base and how the program works. This increases both time and cost. Second, when development and the maintenance are handled by different teams, the original developers often lack the motivation or incentive to write maintainable, well-documented code. This oversight can make future changes more challenging. Third, maintenance teams are often less experienced and may have limited domain knowledge. As a result, they must first learn the system before they can effectively implement new features. Finally, as software ages, its structure degrades due to accumulated technical issues. This makes even minor modifications more time-consuming and complex. All these factors help explain why adding features during maintenance is significantly more costly than incorporating them during the initial development phase. Now let's talk about the concept of maintenance prediction and why it is so important in software development. Maintenance prediction focuses on analyzing a system to identify which parts might cause problems and lead to high maintenance costs. It's about understanding where challenges are likely to arise when changes are made. This process involves looking ahead and assessing the potential impact of changes on the system. By doing this, we can design components that are more adaptable and less costly to maintain. Anticipating changes also help us estimate long-term maintenance and set realistic budgets for ongoing system updates. It is important to note that the acceptance of changes often depends on the maintainability of the components being modified. If a component is difficult to maintain, the associated cost and risks can affect whether a proposed change is approved. Finally, as we implement changes, we need to keep in mind that these modifications can degrade the system's maintainability over time, making future changes even more challenging. Balancing immediate needs with the long-term health of the system is critical for effective maintenance planning. Let's talk about predicting the maintainability of a system, which is closely tied to its complexity. The complexity of a system depends on three main factors. The complexity of control structures such as loops and the decision-making conditions. The complexity of data structures, including how data is stored, accessed, and managed. The size and the design of methods, procedures, and modules. Now, here is the critical points. Greater complexity leads to higher maintenance cost. That's why we aim to keep the system as simple as possible, as long as it performs as expected. Simplicity helps reduce the efforts and cost required for maintenance. But how do we determine if a system is complex or maintainable? We use some metrics to assess maintainability. Here are a few examples. First, the number of requests for corrective maintenance. If this is increasing, it may signal declining system quality. The average time required for impact analysis. This measures how many components are affected by a change request and how long it takes to evaluate them. The average time taken to implement a change request. If this time grows, it may indicate rising complexity. I can think also about the number of change requests. A high number could mean frequent issues impacting the system's maintainability. So, if any of these metrics shows an upward trend, it is a warning sign that the system's maintainability is decreasing. Monitoring and managing these metrics is key to predicting and controlling maintenance efforts. Another way to keep your software maintainable is through software re-engineering. This process involves modifying and updating a system or its component to make it more maintainable or enhance its functionality without changing its core purpose or functional functions. Reengineering is particularly useful when only some parts of a large system require frequent maintenance, rather than the entire system. It allows us to restructure and redocument these components to make them easier to maintain. Now, let's discuss the advantage of reengineering compared to full system replacement. First, reduced risk. Rebuilding a critical software from scratch comes with significant risks, such as error in the specification, delays in the development, and potential business disruptions. Reengineering minimizes these risks by working with the existing system. Second, reduced cost. Reengineering is often less expensive than developing a new system from the ground up, making it more cost-effective option. If you haven't got the idea of re-engineering yet, let me give you an example. Imagine a library system built 20 years ago. It still tracks borrowed books, but lacks modern features like online reservation or mobile access. Instead of replacing it, re-engineering can update the interface to make it easier to use, modify the database to support online reservations, clean and document the code to simplify maintenance. So the core system stays the same, but it becomes easier to use and maintain. By focusing on the parts of the system that need improvement and avoiding the risk of a full replacement, reengineering offers a practical and efficient way to maintain and enhance legacy systems. This diagram illustrates the re-engineering process, which transforms an original program into a more maintainable and updated version while retaining its core functionality. Let's break down the key steps. Source code translation. The process starts with translating the program source code to a modern programming language to ensure it aligns with modern tools. Then we have the reverse engineering process. In this step, the existing system is analyzed to understand how it works. This creates a foundation for further improvements, like documenting the program more effectively. The program structure improvement. The structure of the program is reorganized or optimized to enhance clarity and maintainability. For example, redundant or poorly written code is cleaned up here. Program modularization. The system is broken into smaller, manageable modules, which make it easier to understand, test, and maintain. This step often involves program documentation to ensure that future developers can work with the system efficiently. And finally, we have data reengineering. Alongside the program, the system's data is also updated. This includes restructuring, cleaning, or improving the format of the data while keeping the content intact. At the end of this process, we have both a re-engineered program and re-engineered data, which are more efficient, maintainable, and ready to meet current business needs. This entire process helps extend the life of legacy systems, reduce risks, and lower costs compared to developing a completely new system. Now let's talk about the final concept in today's video, which is refactoring. Refactoring is like preventative maintenance for software. It is a process where we improve a program's structure to make it easier to understand, reduce complexity, and slow down the degradation of the system over time. When you refactor a program, the focus is not on adding new features or functionality. Instead, the goal is to clean up the code base, making it more efficient, readable, and easier to maintain. One important point is that refactoring doesn't change the external behavior of the software. It is all about improving the internal structure. Think of it as tidying up the house without changing the layout or adding new rooms. Refactoring is typically a smaller scale operation that developers carry out continuously as they work on the system. By doing this regularly, they prevent long-term problems and ensure the system remains maintainable. Now, let's address an important question. What is the difference between refactoring and re-engineering? Refactoring focuses on improving the code structure without affecting its behavior. Re-engineering, on the other hand, is a larger process that may involve changes to the software architecture or adding new feature. In short, refactoring is about small continuous improvement, while re-engineering is a more extensive task. That's all I have for you in this video. Before we finish, let me give you an idea of what to expect in the final exam so you can prepare effectively. The exam will consist of two types of questions, essay questions and MCQ. Essay questions, this will test your deeper understanding of the topics. The essay questions will come from Module 3, which is Requirements Engineering, Module 4, System Modeling, Module 6, Software Testing. My advice is to review the questions we have covered in the module videos and the assignment. This will help you prepare for the kinds of essay questions you will see on the exam. For MCQ, this will focus on your knowledge of key concepts. The MCQ will cover Module 1, which is the introduction module, Module 2, software processes, Module 5, design and implementation, and finally Module 7, which is software evolution. For the MCQs, you will find that they are similar to the quizzes from each module, so make sure to revisit those quizzes as part of your preparation. Take the time to review these materials and let me know if you have any questions. Best of luck with your exam preparation. I'm confident you will do great. Thank you for taking the time to watch this video and for being an integral part of this course. As we come to the close of our journey in the software development course, I want to leave you with a final thought. The software we design and build is more than just lines of code. It's a living entity, something that evolves, adapts, and grows to meet the ever-changing needs of its users. It has been a pleasure guiding you through this semester, and I truly appreciate your effort and engagement. Thank you for a wonderful semester, and I look forward to seeing you again in another computer science courses. Until then, take care, keep learning, and keep coding. Bye bye.